Hello everyone. So in the lecture series, I am going to discuss about the flue gas analysis and the calorimetry. So this is the presentation overview. I am going to discuss flue gas analysis and calorimetry. There are two types of calorimeter. So one is a bomb calorimeter. It is used to measure the calorific value of solids and the liquid fuels, and Boyce calorimeter it is used to measure the calorific values of gaseous fuels. And the applications and the impact of flue gas analysis like power generation efficiency, industrial boiler optimization, and environmental compliances, fuel quality certifications, as well as the 3 to 7% of fuel consumption reductions. And finally, I am going to discuss the design thinking approaches, problems such as late manual feedback and solution, real-time accurate data, and criteria automated insights. So first, understand the combustion analysis. The combustion analysis is essential for optimizing the energy systems, reducing the emissions, and ensuring the compliance with the environmental regulations. The accurate measurement technique enables the engineers to evaluate the fuel efficiency and make informed decisions about the system performance. So flue gas analysis, these are the composition and the purpose. The primary components are carbon dioxide, oxygen, nitrogen, and water vapor, and pollutant gases are carbon monoxide and NOx NOx emissions, and sulfur oxide SOx unburned hydrocarbons. The key objectives are efficiency assessment, emissions monitoring, combustion optimizations. So this is the Orsat apparatus. The Orsat apparatus is nothing but it is the device used to measure the volumetric analysis of dry flue gas. So the Orsat apparatus uses the selective chemical absorption to measure the gas concentrations. The gas samples pass through the reagent chambers subsequently with the volume changes indicating the specific gas percentage. So this diagrams represents the Orsat apparatus. It consists of one burette arrangements which is filled with the water jackets to maintain the constant temperature, and also it contains the three absorption flasks like A, B and C. So each flask contains some chemicals for during the experimentation. For example, the flask A is used for absorbing the carbon dioxide. It consists of filled with 1 part of caustic soda with the 2 parts of water by mass. Likewise, for the oxygen absorption, the flask B contains 1 part of borocholic acid with the 2 part of water, and also 24% of caustic soda with the 60% of water by mass. Likewise, the flask C, it is used for absorbing the carbon monoxide pollutant which filled with the cuprous chloride in the hydrochloric acid. So this is the setup. In these arrangements there are three-way stopcock, and also the fused calcium chloride is filled in these purate setups, where this is called the D, that is called the leveling tube, as well as this is called the capillary tube. When the stopcock are in the T in then closed and the stopcock number 1 is opened, the flask A, it absorbs all the carbon dioxide pollutants from the flue gases releasing from the manifold of the vehicles. Once the absorption of CO2 is completed, the level of the water rises through this burette, and also after sometimes it reaches some limit. The height difference indicates the percentage of carbon dioxide. The same procedures is repeated for the absorption of the oxygen as well as absorption of the carbon monoxide. So the absorption sequence are carbon dioxide absorption and oxygen absorption and the carbon monoxide absorption. So this is some other type of modern flue gas analysis: electrochemical sensors, infrared detections, and real-time monitor. In the electrochemical sensor, rapid sensors used to detect the carbon dioxide, oxygen, as well as nitrous oxide and the sulfur dioxide with the high accuracy. So the bomb calorimeter we already discussed. It is the one type of calorimeter which is used to measure the solid as well as fluid type of fuels. So the constant volume combustions, the bomb calorimeter determines the gross calorific value, that is higher calorific values of solid and liquid fuels through the complete combustion under the controlled experiment conditions. Some of the key components are thick-walled steel bomb and water jackets with the precise temperature measurement as well as oxygen supply. The conditions are 25 to 30 bar pressure and electric ignition system. So through this formula we can find the gross calorific value. The gross calorific value is equal to W into delta T minus C divided by M, where the W is the water equivalent and delta T is the change in temperature and also C is the corrections and M is the mass of the fuel. So this is the Boyce calorimeter used to measure the gaseous fuel, calorific value of gaseous fuel. It consists of main parts like gas supply, combustion chamber, heat exchange and the measurements. So through this formula we can calculate the calorific value of the gaseous fuel. CV is equal to MW into Cp into delta T and V gas. Here the M and W is the mass of the water equivalent and Cp is the specific heat of the fuel, delta T is temperature changes and V gas is the volume of gas is consumed. So coming to the design thinking approach, first we need to understand the user needs. So the problem power plant operates struggles with the inefficient combustions leading to increased fuel cost and the emissions violations. The user observations are through the site visits and in many interviews. The users identify that manual flue gas sampling is time consuming as well as results arrive too late for the real-time adjustments. So these are the problems occurs in the case of calorimeter as well as flue gas analysis. The pain points are delayed feedback, inconsistent data quality and also the difficulty correlating the measurements with the operational parameters. So we now going to discuss the problem statements that are core challenges. How might we provide the power plant operators with the real-time accurate combustion data that enables the immediate optimization decisions? So some of the success criteria are continuous monitoring systems, automated data analysis and actionable insights within the seconds and integration with the existing control systems. Some of the constraints are budget limitations, harsh industrial environment as well as minimal training requirements and the regularity compliances. So some real world applications are power generations, industrial boilers and free quality control, environmental compliances. In the case of industrial boilers, the manufacturing facilities employs the gas calorimeters, that is Boyce calorimeters, to verify the fuel quality and adjust the burner settings, ensuring the consistent heat output and minimizing waste case losses. Coming to the power generations, the coal-fired and the gas turbine power plants use the continuous flue gas analysis to optimize the combustion efficiency, typically achieving the 2 to 5% of fuel savings while meeting the stringent emission standards. These are some of the real-world applications. And some of the key takeaways of this lecture series are the analysis methods, calorimetry techniques and the practical impact. In the analysis methods, the Orsat apparatus and the modern electronic analyzers provides the complementary approaches to the flue gas composition measurements. The bomb calorimeter measures the solid and liquid fuel heating values as well as the Boyce calorimeter quantifies the gaseous fuel energy content. So these tools enables the combustion optimization, reducing the fuel consumption by 3 to 7% whilst ensuring the environmental compliances. So these are some of the references I have gone through for these lectures. Thank you for your watching. Thank you.